Today we are in the Thin Film Technology Lab of Dr. B.R. Ambedkar National Institute of Technology, NITJ. So in this lab we have a thermal analysis facility, and for that we have the DSC analyzer supplied by Saturn France. So this analyzers can give you the data from sub-ambient to up to the 700 degrees Celsius. Sub-ambient means from minus 70 degrees Celsius, and to maintain such a low temperature we have this cryo chiller. So this can bring down your sample temperature up to minus 70 degrees Celsius, and if you want the temperature lower than that, then you can have liquid nitrogen facility, which can also be attached to the same equipment. So the first part is that we have to prepare the sample, and to prepare the sample, this is the crucible. So crucible, you are not supposed to touch it. So practically you have to use the tweezer for that and take out one particular crucible. So let's say this is of 120 microliter in the volume. So first you have to weigh the crucible and make sure that you have a semi-analytical weighing balance, means at least 0.1 mg. So once you weigh the empty pen, so after that you can note down what is the empty weight of the pen, and then probably you can tear it, and then after you have to put your sample. So sample should be in such a way that this complete alumina crucible need to be filled from the bottom side, so that you should have a perfect contact that your sample is touching entire bottom. So you have to fill that amount, and maybe you can recheck it, your weights, what is correct, or have you teared it properly or not. If not, you can re-tear it actually. So you can see that it was perfect tear. Now you have to put the sample in there. So for time being, for this demonstration purpose, we are taking a sample of polycaprolactone. So you can see that sample size is some polymers are big, some is a smaller one. So sometimes you need to cut the sample actually. So let's say we have these two samples, and out of that we need somehow 40 milligram. For this system we need 40 milligram of the minimum weight in order to completely cover your bottom of this crucible. So you have to charge it here and put it inside that. So you see that this quantity is 60 milligram, so slightly higher than 40. So either we can decrease this quantity or break the sample. So cut the whole. So since the sample size was bigger, so we have somehow cut it down with the help of the knife. Now we can pour this quantity, maybe this particular sample there. So if you can re-tear it if somehow it fluctuates, because so if you will pour it here, so you can see the sample quantity is 53 milligram or something, 54. So we can go ahead that because the reason about this, this actually crucible is very big in the size. Actually this is something 120 microliter, so you can have such a large quantity also as well. So once it is prepared here, now the next part is that you have to cover this particular crucible. So for that we have a crucible lid, and there you you can cover it with the help of this crucible lid and put it here. And this is actually you have one is cramping tool. So here you can take this and put this entire crucible here, this one, and so this is for a smaller quantity actually. So this is for the smaller quantity 30 microliters. So this side is for 120 microliters. So you can find the difference. This is now fully covered. Now on top of that, just put this lid, and this is the clamping tool. So you put it here on top and just press it hard. So this way you are just locking it. So this way now your sample is ready. So this you can say now your sample is fully tight here. So nothing is. This would make sure that while you are heating the sample, so sample will not spill over the furnace or the sensor. So next part is that we will show you how to mount it in the DSC analyzer. We want to mount the sample. So this is the part of the furnace you have. So you have to take it out carefully. And this is the covering, so you have to remove this again carefully. And now you can see from here, these are the sensors. You can see that one sensor is this side, another is this side, another. So there are three sensors, and this is the reference crucible. So it should be made up of the same material. So we have currently aluminum crucible, so this is also the aluminum for the reference, and this entire accessory is the furnace. So it can go up to the temperature actually 800 degrees Celsius. Now we have to mount the sample here. So this you can see, this is our sample which we have prepared. Now this one need to be mounted here carefully, so that it should be inside the three sensors carefully, and don't press it hard, otherwise this sensor will break down. So now you can see it is completely horizontal, and you have mounted it carefully. After that, do not forget to cover it. So while covering it, this covering will make sure that you are maintaining a entire covered chambers. And now for that, just to maintain the temperature of this thing, you have two gas arrangement. One is for nitrogen gas, one is for argon gas. And once it is done, so you can just carefully put this cover, outer cover, and after that you can slightly press it down, don't press it hard. So this is in the case that if you want to do the analysis from ambient temperature to 700 degrees Celsius. If you want to go to sub-ambient part, so in that case, that particular place, you remove it, and then you have to connect it to this cryochiller part. So cryochiller here, from here the cooling comes, and for that this will cool the entire furnace. So you can put it on this way, and that will make sure that you are connected to the cryochiller. So this you need to have only that when you need to go for sub-ambient, means lower than 0 degrees Celsius, otherwise you don't need it. Testing for polycaprolactone. So we know the temperature of polycaprolactone is nearly 100 degrees Celsius. So we need only ambient conditions or more than that. So we can cover it here first, and that's all first. So now we have to start the data acquisition software. So for that you have to click on this, and it needs your admin password, so you can give it. And now from here you can see that window what we have here. So on this y-axis you have the sample temperature, and this side you have the heat flow, how much heat you are providing to the sample. Now on this one you have the furnace temperature. So furnace temperature in the red color, heat flow is coming in the blue color actually. So you can come to know what is happening. And the red one is your sample temperature. So you can see that what is happening between the two. And bottom axis is the time. So you can interchange this time with temperature. So if you want to have for temperature here, you can select it maybe furnace temperature, or maybe select it for sample temperature here, or generally people go for time in the beginning, so it looks nice. Now we have to put the experiment part, so we have to click on experiment. Now you say the by default this gives the experiment name and date and time, but we have to assign our own numbers, so we can go for experiment properties, and then we can, this is the sample ID actually, so you can define if you want date and time, keep it like that. If not, you can change according to you. So we want to say that's a polycaprolactone. So you can give that name. So you give the sample name, and after that you have to put the quantity of the sample, how much quantity you have taken. So we have taken there 54.2 milligram. If you can weigh the quantity in gram per mole, you can do that part also. But generally, all weighing balance give the mass in milligrams or grams. So you can put that quantity. After that, you have the option just to choose what type of aluminum crucibles or crucibles you have. You have 100 microliter, 170, 30, and all those. So you can choose according to that. And we have aluminium. First is alumina actually. So these were alumina one. You have platinum one. You have steel. You have tungsten one, and then you have alumina. So alumina we have 120 microliter. So we can select that one. So this is the sample in the nomenclature part. So once we enter the sample details, that the sample name and quantity and type of aluminum crucibles and its volume, then we have procedure summary here. So you can write a comment that how have you prepared the sample something. So you can write the summary here. Further, you can write here, these are your safety guidelines. Let's say you want to have a test sample something, and temperature, carrier gas, what you are taking, air, nitrogen or argon. So you can select it from here. And this is the CFT temperature. So for this furnace currently which we have, the maximum temperature can go up to 710. So for safer side, we are not allowed to go more than 600 degrees Celsius. So that temperature we can define from our side. Let's say we want to make it safer side 500. So if we have fixed it 500, so somehow in your heating or cooling zone of the sample, if you will give us a temperature of 600 or 510 or 50, it will not go to that one, because you have kept a cap of 500. It will give the warning that there something is wrong with the sample analysis. So these are things. So our carrier gas 2 is actually the nitrogen gas we are using, and carrier gas 1 we are not connecting. It is connected to the argon actually, so we are not taking that part also. So we have carrier gas 2 is nitrogen only. So once you have fixed up all these parts, after that you have to go here, you have to put your temperature zones. So means we need a heating zone, cooling zone, standby temperature. So we can put a standard zone here. Now if you see here, you can find this thing here from where the temperature will go, your final temperature, what should be the heating rate, and how much should be the time. So if you fix up the time, your heat or let's say heating rate is fixed, time would be calculated automatically. So let's say first part you want to have a temperature currently, let's say you want to have it from room temperature. So if you are not maintaining with some air conditioner or something, in hot climate room temperature you can put maybe 30 degree, maybe 35, Or let's say in cold climate, you would have a temperature, let's say for 15 degree or due to cold weather. So you can put that temperature. It's better to put the temperature which is of atmosphere. No need to put a temperature which is not there in the atmosphere, because you will not get the data in that range. Or you turn on the chiller if you want a temperature lower than this or something less than ambient, so turn on the chiller for that. Otherwise no, you are always expected to have a temperature near to atmosphere only. So let's say the first one we want to go for time being, our room temperature is 30, and we want to put 30 to 30 just to have this 30 to 30 means you want to maintain the sample temperature 30 for, let's say, for a time being of 2 minutes. The purpose of this, it will just make sure that your entire sample, because you have put a sample which have some actually a lumps or a powder, and some may have a temperature outside environment, some will not have it. So if you will give a temperature for some time, it will make the uniformity of the temperature of the entire sample. So you can hold it at maybe for 2 minutes. That is sufficient time. So once you gave it 2 minutes, so you can turn on the valve here. So you both the valve is on. So here, if you are not clicking here, it means the carrier gas 1 is on. So 1 is argon which we have not connected. So we are clicking it here. It means the carrier gas 2 is on here. And we should make sure always the fan should be on, because fan is the only thing which will control your temperature. So first you maintain the temperature of the sample 30 degree. After that you want to have from, let's say, 30 degree, you want to go ahead for, let's say, 200 degrees Celsius. If you don't know the much about the sample, that where would be the glass transition temperature of the sample, so you can give it 200. Now here you have the choice. What should be your heating rate? So let's say you want to have a heating rate of 10 Kelvin per minute. So it will automatically calculate the time. Currently it is in seconds, so you can convert it to the minute. So you can say it is in the 17 minute actually. So it will calculate automatically. Now let's say at 200 degrees Celsius, again you want to maintain some temperature so that entire sample will get the 200 degrees Celsius. So you want to hold it at 200 degrees Celsius. Let's say you want to hold it for 2 minutes. So you can do that part. After that you want to cool down. You want to see that what will happen on cooling. So let's say from 200 you want to cool down for till 30 degrees Celsius. Let's say you want to have the same cooling rate. You can have a different, choice is yours. So you can have a different heating or cooling rate. So currently we are putting a heating and cooling rate is 10 Kelvin per minute, and based on that you can say the total time needed for this system is something. So total time would be calculated for here, 34 plus 4 is 38 minutes. So 38 minutes is the time for the sample. So once you have fixed all this property, now you can go to this side is start. You can directly click here. You can start the instrument would start. Or before that, you may go to this menu part here. Go back. So you can see here real-time drawing. How this is how the reference or the data coming from furnace for the time being. It is off actually. You can see here the furnace parameters. These are some PID controller things. So we don't want to interchange or change anything here. Manual program here. So this you can do before in the beginning. You can turn on the gas here. If you want to modify, you can modify here gas. Turn on the fan, and now you can see that some noise has come in the DSC. It means you have turned on your fan. So that what will it do? It will take out the excess air from this pipe which are connected, which are giving you the gas supply to your furnace. So sometimes excess pressure build up, so that will be taken care by this fan only. Too much excess wear, maybe disconnect your connections. So once it is done, and now you can see here the security temperature is clearly mentioned here 710. So we have set in the base program means earlier, that is 500 degrees Celsius. So this is the part you have to make sure in the beginning. Now we have here two gas connections here. One is the nitrogen gas, one is the argon gas. So it depending on the environment in which you want heating or sample analysis to be done, you can select the gas. So let's say this is for the nitrogen one. So you have to open the valve here first, and with the help of this control valve, you have to set the temperature is 2 psi. So 2 psi is the maximum guidelines fixed by the instrument. So you can fix it up with this help of this valve. So you can close it, open it till it become the 2 psi. So slightly up and down would work, but not very higher than that. So once you have set everything, your the sample parameters, your heating and cooling zone temperature, it means the standby temperature, your heating zone 32 to 200, then the standby again at 200, then 200 to 30 degrees Celsius. You have turned on the gas carrier 2 from here, and this is for fan. Everything is on, and then you can see that if you see here the green signal means your equipment is on, and you can see here you can put your hand here, so that can give a feel that instrument is also on, fan is also on, so nothing will go wrong actually in that way. And after that you have to just click here the start button, and from here just click on start, and you can find here the signal here. So this is what you are getting here, your sample temperature, and this side is the heat flow. So heat flow is coming in this blue color, 0.5 milliwatt, and this is how the temperature is. 27 is, you can see, the temperature of your sample actually currently here. So you can observe it for time being, and let's see how the response is coming. Now to look the graph better, you can maybe put here 10, so you will see how the things are going on. This is what you can see. This is your set temperature. This is what you want, that for 2 minutes you want at 30 degree. After from 2 minutes you want to increase 10 degree, 10 Kelvin per minute, and you have to go for up to I think 17 minutes. So it will keep on continue till you reach to the 200 degrees Celsius. So that much is not expanded here, so you can do that. And this red line is the line of the sample temperature what you have currently. So red line will propagate as the time will pass on. So that would be your sample temperature. So you will see that your experiment is going on here. You can see how this your sample temperature is going on. Now you can see from here sample temperature has been reached to the 53 degrees Celsius. So in the meantime, in the background, you can do your sample analysis or treatment in beginning, so you can minimize this window, and then you can go for this data processing. So here this would need your. Now from here you can go to this one, open zone files, and you can take your any samples which you have already done, or let's say we want here, let's say some case of coating here, we have this sample of polymer film, and now you see the graph here, so you can change this axis from sample temperature to time, and now you see here there are no very much sharp peak and all this, so those comes only in case of solid material where there was completely a sharp peak. So let's say you can have zinc one, you can see the how the peak are completely a sharp change. Now you see for this side there are no one. There the change from here, but not abruptly. So in that case also you can find your TG just the same procedure. So click on that on this means temperature profile curve and go for glass transition. Select the point anywhere at two ends here. It will all means calculate your glass transition temperature here. So TG is coming something 71 degrees Celsius. So you need not to worry. So if you can keep on changing these points also here and there, your this calculation here doesn't change. So if you see here, so either you select this, move the point slightly here and there won't be any change in this TG. So that is the beauty of this particular software. It automatically take care and calculate from the tangent where the sharp change comes. So no matter where the points are, so you can calculate it automatically. Now let's say you want to calculate here enthalpy of fusion here. So you can again click on this one. So and then go for baseline construction. So click on this and then select the 2 point where you have a dip, and this based on that you can calculate here this enthalpy of fusion, that is 3.286 joule per gram, and then you have a starting and closing ends here from where this transition taking place and completed, and based on that you will get this particular part. So we can see that at the end of that time period 38 minutes, you can see that how beautiful graph you got it actually. So first 2 minutes you have standby temperature which we have maintained something 30 degrees Celsius in the beginning. So this is the temperature line. Red line is the temperature one. So you have the temperature here. And blue line is heat flow. So you can read this axis for there, how much heat the sample is getting absorbed. So therefore all these things are in minus only. Because in the beginning the sample is absorbing heat, so all these values are minus, and in cooling zone sample is releasing the heat, so therefore things are in plus here. And this you will see there the sharp change here. So this is somewhere in this you have a glass transition temperature there. So we can do the treatment of this particular sample. So if you will go back here, so you can again open the zone file from here and you can locate your sample from here. So this is the sample which we did just now, and this will look like here. So this is in terms of some temperature axis here. So you can say the TG is somewhere here. So this we can read from here. So we can change this thing to time first. So this will look like that. Now if you want to find the TG, so you can click on that, go to your glass transition temperature, and you can select these 2 points where your transition ends. So you will find from here the TG of the sample is 77.08 degrees Celsius. So there would be somewhat differ from your theoretical value, because this is not a theoretical sample, actual sample. Sometimes may have some impurity, maybe some different molecular weights. So TG is a strong function of molecular weights and composition on chain length. So it will vary from sample to sample. So it's better to find your own TG for each sample. And now let's say you want to find the enthalpy of fusion for that. So you can click on this sample again and go for baseline construction here. So you can click here from where the transition is, and from here you will find the enthalpy of fusion here. So this is your CP value. Enthalpy is that one, 73.969 joule per gram. And from here you can find this from where the transition starts and ends. So it started this here 54.43 degrees Celsius, it ends at 98.72 degrees Celsius, and the time consumed during this particular time is 5.6 to 9.9 minutes actually. it start at 5.6 minutes and it ends at 9.9 minutes. So based on that you can calculate this enthalpy part also. We did this sample, the previous sample we did here based on 10 Kelvin per minute heating. So if you want to go for slow heating, sometimes you will miss up this transition part, may not be that much sharp. So let's say if you want to put the high heating rate, so let's see what will happen in case of high heating rate. So you have previous sample here which you have loaded property here, all properties are there, sample is here, crucible is here, your zone temperature, everything is fine. Only thing you want to change here the heating rate from 10 to you want to make it 20 Kelvin per minute, and let's see what will happen in that case. So for that you need not to do anything, you have everything, you can clone the experiment from here. So this is now cloned one, you can change the name here, sample property here, this is copy of the previous one. So this you want caprolactam here, only thing you want here, the heating is now double of previous one. So you can say that 20 Kelvin heating here, Kelvin per minute. So that is the new heating, 20 Kelvin. Rest of the things are same, so you are not doing anything here. Only thing on this heating rate, let's say you want to make it 20, so you can make it 20 here, and same thing you want to for cooling part, you can make it 20, cooling here. Rest of the part is same. So let's say what will happen in case of very fast heating, and that we can practically observe here now. So we can run the sample again and let's see. You can see that graph in that case, there the fastest change you can see the TG. So TG has come from here, so you can change the axis here from time to temperature. So you can see that this is the somewhere here again, something 57 something. And now if you will see the graph side, so this part your heating zone and you are heating it up to 200 something. And after that there's the cooling part here. So cooling part in this particular software shows to the upside here. So from here the cooling starts. So this is the cooling curve here. So it will keep on going here and you will find another sharp peak here. So that will give your enthalpy of crystallization part, a crystallization zone. So this analysis of the same sample we did for high heating rate at 20 Kelvin per minute. So you see in this case this peak is slight sharp here because time taken is very short. So this one is here as compared to the previous one. You can see this is the previous graph here, and this is the new graph here. So you can see the change is a bit faster, and you can see that okay, TG is here. So we can do the analysis of the same thing again. So this same sample we did at high heating rate, 20 Kelvin per minute, and you see this particular change is very sharp now as compared to the previous one. So you see the previous one here, that peak is very broad here. Now it is very narrow, so you can see the sharp change. So you can have a further high heating rate, and the high heating rate can give you the sharp change faster. Slow heating rate will make this peak broader and broader, and as far as that TG value is concerned, I hope there won't be much change. So if you will open that sample file, so this is now for 20 Kelvin per minute one, and so in that way if you will see from here, you see that this is the sharper one here. Now you want to find TG, so you can select the TG from here, and you can choose maybe the point here and maybe at this end. this place, and you see there are no change in TG here. This is TG. Here is coming this 56.14, and for the previous one here, for this sample here, this was the TG again. Now the TG, you see that its value is coming something 77 something. So you see that your heating rate would also matters. That same sample we want to do it again a very high heating rate, 30 Kelvin per minute, and let's see the how the result will come for that case. So let's see for that. So it would be a very fast one. So here we did at further at high means heating rate at 30 Kelvin per minute, and you see the graph, you cannot find any change. So actually you, because the heating rate is too much fast, and you have missed up that particular zone where transition would occur, because that's the reason for here. So it is always means advisable just to go for a reasonable heating rate, or you can say practically a slow heating rate, that is 10 Kelvin per minute something. So that is the point here, because here you will see there are no sharp change there where you can identify this part is the transition zone something. So if you go to the processing part again, and if you can open this particular file, so you will come to here. So there's nothing here. Here you have a sample temperature there, and you will not find anything here. So you were totally confused that what wrong with your sample. But there's nothing wrong with your sample. Only thing you are not giving is time. There's something it's called the relaxation time and experiment time. If your experiment time is such a fast that it is overcoming your relaxation time of the sample, then you will not find any change actually. So it means your experiment time should be such that it should be something is in between or close to the relaxation time or lower than that. Only then you can find a change or glass transition part. Otherwise you won't be, because you will find it is a continuous heating, something like that. You will see here is gaining the energy, and there's something like that, and there's again gaining. So here you are heating in the beginning, and here you have the some change here. After that is here some change, and then it is decreasing and decreasing. After that is gaining some energy further. So if you will find let's say TG for this sample here, just like means normal exercise here, if you can say this one, and if this one is your change, so you can say the TG 137, which is not possible, it's impossible, because you are not doing something correct. So this end maybe somewhere here part. So here it could be slightly reasonable, but you are not you cannot be sure about this point, because here is not ending of the session, so it's further keep on going and going. So you are not advised to a excessively high heating rate, and therefore you 10 heating rate is always advisable, or moderate heating rate. It will give everything fine and no sample relaxation, and as a general rule you can find 10 is good one. Otherwise you can go for 20 if you want a faster change, but still you see the nature of the curve here had distorted a lot compared to here. Here you find a change here, then decrease, the change occurs, transition occurs and ends. So this is good thing. This graph would be much more better if you can provide a heating rate further lower, maybe a 5, maybe 1. Then you will find a straight line here, and there is a perfect graph here. So that need to be taken care while fixing the heating rate.